Hello, my name is Zach, and this is my cosmology assessment. Starting off with CMB properties, first we'll be taking a look at the benchmark model and what it looks like in the CMB simulator. So as you can see, the density parameter for normal matter is at 0.05. At dark matter, it's at 0.25, and dark energy is at 0.7. As you can see, the universe similarity is pretty close to 100%. Now moving on to the simulated universe, I chose with different parameters. So I chose a very high density parameter for normal matter, way higher than the benchmark model. So I chose 0.8 for normal matter. The density parameter for dark matter is lower, it's at 0.1. And the density parameter for dark energy is much lower than the benchmark model at only 0.1 for this universe. So the simulated universe has much more normal matter, meaning it has much more baryons. As you can see down here, the universe similarity is only at 25%, so it's not very much like our universe at all. In comparison, the hot and cold spots seen in the simulated universe with a much greater normal matter density parameter have a higher contrast in color, meaning that the hot spots are hotter and the cold spots are colder. Furthermore, comparing the power spectrums, the amplitude of the first peak in the simulated universe is actually greater than that of the benchmark model. This is because a higher baryon ratio means that there's a slower speed of sound in that photon baryon fluid that we had after the Big Bang. The L of the simulated universe is greater at about 360, which corresponds to a smaller angular scale of about 0.5 degrees. This is different than the benchmark model where the angular scale is at about 0.7 degrees. And again, this is due to the fact that there is a higher baryon ratio. So the simulated universe has one common characteristic that our benchmark model has, and that is a similar geometry. So although the two universes have very different density parameters, the sum of these parameters in each universe adds up to about 1. And since the sum of these parameters is 1 for both universes, both the simulated universe and the benchmark model have a flat curvature. Moving on to some of the early universe properties. First, we're going to be calculating the baryon to photon ratio. So starting from writing equation 8.3 and module 5, class lecture video 3. So first, what we do is find the energy density of baryons. And then moving on, we can find the number of baryons. And then finally, you can compare that to the number of photons and calculate your baryon to photon ratio, which we use eta to simplify. And that value comes out to about 1.03 times 10 to the negative 8 for the simulated universe. Comparing this to the benchmark model of about 6 times 10 to the negative 10 baryons per photon, this value is definitely greater. It's about 17 times greater, but as you can see, there's still much more photons than baryons. Next, we're going to be calculating the temperature of recombination. Module 5, class lecture video 6, gives us the following equation. Temperature of recombination is Q divided by KB times ln of 1 divided by eta. So then plugging those in the next step, that yields a temperature of recombination of about 8,581 Kelvin. Next, factoring in the Saha equation, that's going to give us our final answer, which is 4,500 Kelvin for the temperature of recombination. Again, comparing this to the benchmark model, which gives us a value of 3,870 Kelvin for temperature of recombination, you can see the temperature in this simulated universe is greater. Next, looking at the redshift and scale factor at recombination. Module 2, class lecture video 5 gives us the equations of cosmological redshift, which is the redshift is temperature of recombination divided by temperature of the CMB today minus 1. Plugging that in, you get 2,600 for the redshift at the time of recombination. And then moving on to the scale factor at recombination, that's just going to be 1 divided by 1 plus the redshift at recombination. Plugging that in again, you get 3.8 times 10 to the negative 4. Comparing these to the benchmark model, which has values of 1,380 for the redshift, and for the scale factor, it has value of 7 times 10 to the negative 4, which we learned from module 5, lecture video 6. You can see that the simulated universe has a greater redshift, but the benchmark model gives a greater scale factor at this point, which is the point of recombination. Moving on to expansion history. So I chose a moment of matter domination. It's going to be about 0.3 times the Hubble time. Calculating the scale factor this time. So A is going to be plug 0.3 in, and you get 0.45 for the scale factor at this moment in time. Obviously, the benchmark scale factor for the scale factor is going to be 1. And then looking at the redshift at this time, it comes out to 1.22. Again, compared to the benchmark model, which just has a redshift value of 0 today. Now calculating the expansion rate at this point. So calculating a single dot, that's going to be 2/3 times 0.3 to the negative 1/3 power. And then taking that one step further, calculating h, which is a dot divided by a. So you just plug this here, divided by a. It's going to give you a value of 2.22. Next, calculating the critical density. So module 3, class lecture video 5 gives us the equation for calculating the critical density, which is going to be 3 times c squared over 8 pi g times h squared. Plugging all of those numbers in, you get 7.89 times 10 to the negative 26 kilograms per meter cubed. Now looking at the expansion future of the simulated universe. In this universe with a much higher normal matter density parameter, again of 0.8, the fate of the universe will end much like that of the benchmark model. This means that the universe will always continue to expand, as opposed to reaching a maximum and beginning to contract, resulting in a big crunch. Although this universe will continuously expand, it will likely take more time to expand in comparison to the benchmark model due to the extreme difference in various density parameters. So in other words, both universes are going to expand endlessly, but the benchmark model will actually expand faster than the simulated universe. Next, comparing this with data sets. So here's my point right here, this red circle, all the way at the bottom right corner of the plot. As you can see, it's nowhere close to this gray area, which is where all the various methods of measurement intersect. And although there is not an agreement with the experimental constraints shown on the plot, This point does still fall on this line right here that indicates a flat universe, which makes sense. And that is it. Thank you very much for watching.